So welcome to this latest video 162 Maths, and in this video we'll be going over the GCSE Maths higher topic of basic probability and relative frequency. Now in this video we'll go over what it is you actually need to revise, going over some of the key concepts, as well as then before going through some past exam questions. Now a copy of the exam questions that we go through in this video are available for you to download by click on the link in the description, which I strongly recommend that you do to have an attempt at, so you can see what areas you're good at and which ones you're not so. Now before we get started working through some questions on basic probability and relative frequency, let's just have a quick refresh on some of the key aspects of basic probability and relative frequency. And this will be good if you're one person who likes to make notes, and I certainly would include these in your notes when revising. So in terms of relative frequency, now relative frequency is about experimental probability. Now there are two types of probability. One is theoretical and one is experimental. Now theoretical probability is based on maths. It's based on the notion of the number of times an event can happen over the total number of times. Now how relative and experimental probability is different is that it's based on actual physical results. So if you were to roll a die 6 times, then theoretically you should end up with a 1, 2, 3, 4, 5, 6 appearing once. However, if you physically rolled a die 6 times, then that's going to be incredibly unlikely that you will have one of each number. So theoretical probability is where what the maths is telling you. Experimental probability is what an actual experiment or past an experiment has actually told you. So to work out relative frequency, it's the number of times the event has actually happened over the total number of times, and this usually comes in the form of a table where you are picking out a frequency and dividing it by the total frequency, which will therefore give you the relative frequency. Now the frequency of an event after n trials. So if you've got a table completed, a common question that gets asked is, if you did something, let's say 7,000 times, how many times would you expect an event happening based on what has happened in your little experiment? Now to do this, you find the probability from the table, and then you then multiply that by the total number of trials. The next thing we move on to is a bit of vocabulary. Now independent events are basically where the result of one event has no impact on another. So the probability doesn't change. In some way it becomes fixed. So for example, if I roll a die twice, then what I scored on the first roll is not going to impact how I did on the second roll. If I, let's say, had 2 exams on 2 consecutive days, those 2 events might not be independent, even though they may be for different subjects, because if I do well in my first exam, it might put me in a good mood to do better in the second exam. However, if I did bad on day 1, it may mean that I'm going to do bad on day 2 because I'm going to be mentally scarred. Ultimately, it could be the opposite, where if I do bad on day 1, I might do better on paper 2 because I need to make up for it, and I worked that a little bit harder because of what paper 1 was such a disaster. The next word we move on to is mutually exclusive. Now mutually exclusive basically means that these 2 events or multiple events cannot happen at the same time. So for example, you rolling a even number and an odd number on a die can't happen at the same time. And so the probability of a mutually exclusive events will always be 0. The next type of event are exhaustive events. Now this is where all the probabilities all add up to 1 because there are no other possible events that can happen. So an example of this would be if I was to roll a die, then the numbers 1, 2, 3, 4, 5, 6 would be exhaustive events. So if I just say I roll a die, then the only possible numbers on a regular die are going to be 1, 2, 3, 4, 5, 6. Now depending on whether that die is biased or not, but ultimately these are the only numbers that I can get. 1, 2, 3, 4, 5, 6. So that means that regardless of what the probability, whether it be fair or not, it basically means that these probabilities here need to add up to 1 because there are no other possible numbers I can get. I can't get a 2.5, I can't get a 7, I can't get an 8. I can only get 1, 2, 3, 4, 5, 6. So if I add up each of those probabilities, it should add up to 1. So therefore we call these types of events exhaustive events. The next thing we move on to, that if events are independent, then if you want to combine 2 events happening, so A and B, then just remember that the word and means multiply. And if you want the probability of event A or B, then here we add the probabilities. Now the reason why we multiply when we're ANDing is because by including 2 events to happen, the chances of those two, we're increasing the events because we want two things happening. Before we only wanted one thing happening, now we're wanting two things happening. So that's then going to increase the probability. Now, when we're using or, we're actually saying that we either want multiple events happening. So if therefore, then the probability needs to be added together, because that's going to increase the chances, because we're adding more options that we're actually going to be happy with. So it's really important that you get your head around, and I would recommend that when revising these types of words related to probability is always try and have an example that makes sense in your head, which will make understanding when these words come up in exam questions that just a little bit easier to understand. Now, before we get started working through this topic test, a little reminder that this test is available for you to download by click on the link in the description below, and I strongly recommend you have an attempt at these questions just to see your initial understanding of the questions and also to see if you get them right. So looking at question 1, it says that a dice is rolled 50 times and it lands on a 4 12 times. Work out the probability of the dice landing on the 4. Now typically you would say this is going to be 1/6 if this was theoretical probability, but because this is based on, they want you to give the probability based on past results, then what we need to do is we need to use this bit of information here. So the probability of it rolling on a 4, well, out of 50 it landed on a 4 12 times, so the answer then is 12 over 50. As it's only worth 1 mark, you'd be fine giving that answer, but if you wanted to simplify, which it does, it would be 6 over 25. So any of those two fractions would be fine in your answer. Moving on to question 2, it says there are 20 counters in a bag, 8 of them are purple. Write down the relative frequency of picking a purple counter. Well, there are 8 purple counters out of 20, so the answer then is going to be 8 over 20, which can be simplified as 2 over 5. So again, for 1 mark, any of those answers will be fine. The one time where I would say they need to give you a simplified fraction is if they ask for it, or maybe if it was worth 2 marks. Question 3, it says, what is the relative frequency that represents 12 successes out of 25 trials? Well, again, it's just going to be 12 over 25. So never try and make questions more complicated than what it actually is. Sometimes the wording can be a little bit confusing, but the answer can be so much simple. Moving on to question 4, it says that a fair spinner has 4 sections labelled A, B, C and D. Jackie says that the probability of it landing on a C is 1/4. She also says the probability of it landing on a C twice after 2 spins is a half, because a quarter plus a quarter is a half. Explain the mistake that she has made. Now the mistake that she has made is because she wants a C and a C, and is where we multiply, not divide. So the error is that she added a quarter with a quarter instead of multiplying. So something along those lines would be absolutely fine. Moving on to question 5, it says the probability that a bias spinner lands on a 4 is 3/5. The spinner is spun twice. What is the probability of the spinner landing on a 4 twice in a row? So again, we want the spinner landing on a 4 the first time and the spinner falling on a 4 the second time. So it's going to be 3 times 3, which is 9, 5 times 5, which is 25. Then just double check to make sure that simplifies, which it doesn't. So there is my final answer. Moving on to question 6, it says that a fair coin is spun 3 times. Work out the probability of a spinner landing on 3 tails. So here we've got the coin spinner, being spun once and landing on a tail is half, and that to happen again, and that to happen again. So it's going to be a half times a half times a half. 1 times 1 times 1 is 1, and 2 times 2 times 2 is 8. Now moving on to question 7, it says the padlock has a 4-digit combination. Each digit is a number from 0 to 9. The digits may be repeated and the code starts 798. Ryan knows that the last digit is a prime number but not 2. What is the probability that he chooses the correct number? So for this, if we write down the prime numbers between 0 and 9, well that's going to be 2, 3, 5 and 7. Well, we know that it's definitely not going to be 2. and there are 10 numbers in total. So the probability that Ryan's going to pick the correct number is 3 over 10. Then moving on to 7b, it says the code gets changed. The first digit is 28. How many possible codes are there? Well, for the third digit, there are numbers from 0 to 9, which is 10 numbers altogether. And for the fourth number, that could also be any number between 0 and 9. So again, that's another 10. So it's going to be 10 and 10. So it's going to be 10 times 10, which is 100. Moving on to question 8, it says that a coin is thrown repeatedly. After 20 throws, the number of heads were recorded. And it says complete the table. So for this missing value, what we need to do is work out the relative frequency, which is going to be the number of times the head came up, which is 44, over the total number of throws, which is 80. So it's going to be 44 over 80, which is 0.55. Then all that's left for me to do for B is to plot these values. So if I just zoom out a little bit so I can see the table and the values, and I can just about see them there. So at 20, it's at 0.6, which is here. At 40, it's at 0.55, which is roughly around about there. For 60, it's at 0.6. And for 80, it's at 0.55, and for 100 it's at 0.58, which is about there. Now we don't need to join those points up, we just need to generally know whereabouts it comes about, so I'd say that will be fine in terms of the plotting. Then for question 8c, it says which relative frequency gives the best estimate. What's that there? Oh, it's just reset, so let's just quickly go through all the answers again. There we go. So which relative frequency gives the best estimate for the probability of getting heads? Give your reason for your answer. Well, the best one is going to be 0.58, as the more trials you do, the more accurate the relative frequency. So the key thing to remember is that if you have a big, and I mean a large number of trials, then your theoretical probability will match up with your relative frequency. So in terms of those theoretical and experimental probabilities will tend to become very, very similar if you increase the number of trials on a relative frequency or experimental probability event. Moving on to question 9, it says that employees were asked how they travel to work. The table shows the relative frequency of their results. Work out the value of X. Now, again, all these events are exhaustive in the fact that there are no other forms of transport that these employees can take. This is it. So it's only 5 options and there are no other options. So that basically means that all of these probabilities need to add up to 1. So then if I then do 1 take away each of these probabilities, so 0.25 minus 0.4 minus 0.1 minus 0.05, that should give me a value of X, which gives me the final answer of X equals 0.2. For B, it then says work out the probability that randomly chose employee travels by bus or by train. Now, bus or train, well, if I look at the probability of a bus, which is 0.25, or means add, and we want the probability of a train, which is 0.05, which is then an answer of 0.3. Then for question 9c, it says 80 employees travel to work by car. Work out how many employees travel by bike. So if 80 equals a relative frequency of 0.4, then what I want to know is what's the frequency when, which is a bike. So that's the probability of a bike. This is a car. So if 0.4 is 80, what is 0.1 going to be? Well, to get from this number to this number, I divide by 4. So I need to divide by 4 for this one. So that's going to be 20. And that there is my final answer. Moving on to question 10, it says that a coin lands on a head 120 times. The relative frequency of a head is 0.6. Work out the number of times the coin was thrown. So here what we've got is that to work out the relative frequency, it's the number of times it happened over the total number of trials. That's the general formula for relative frequency. Now, this number I know is 0.6, and this number I know, which is 120. So if I just call this, which is what I want to call x, so what I know is that 0.6 equals 120 over x. So x equals 120 divided by 0.6, and that gives me an answer of 200. Another way of looking at it is knowing that 60% is 120, so then what's 100%? In which you should get the same answer of 200. Then for question 11, it says that a spinner can land on red, orange or yellow. After 450 spins, the relative frequency of red is 0.38, relative frequency of orange is 0.26. Work out the number of times the spinner can land on yellow. Well, if all the events of these three colours are exhaustive, then to work out the probability of a yellow, or the relative frequency of a yellow, is going to be equal to 1 minus these two probabilities, which is 0.38 minus 0.26, and that gives me an answer of 0.36. So then to work out the number of times it's going to land on the yellow, it's the total number, which is 450, multiplied by the relative frequency, which I've just worked out, which is 0.36, and that gives me an answer of 162. Moving on to question 12, it says that Harry has a bag containing 4 different colours of jelly beans. The jelly beans are yellow, green, red or white. The table shows probability of selecting each colour. A jelly bean is taken from the bag at random. Work out the probability that the bean is white. So let's have all work out these. Now, as you can see in the table, I don't know the numerical values of the probability, but I have got some expressions. So one thing I know is that all the events of those colours are exhaustive. So these probabilities need to all add up to 1. So then what I've got is 0.24 plus 5x plus 2x plus 4x plus 0.1 equals 1. Now if I neaten all of that up, I get 11x plus 0.34 equals 1. So then 11x equals 0.66. So then x equals 0.06. So then once I know what x is, I can then work out the probability of a white, which is 4x plus 0.1. Well, if I know that x is 0.06, it's going to be 4 lots of 0.06 plus 0.1, which gives me an answer of 0.34. Then moving on to question 13, it says the table shows information about the variety of greeting cards in a shop, and it says a card is chosen at random. The probability that it's a get well card is 1 over 40. Work out the probability that a birthday card is chosen. So let's have a look at all the information we know here. So again, we know that these are the number of cards, not the relative frequency. So that's really important that you do spot that. Unlike all the other questions, this is the number of cards rather than the probability. So what we know is that 5 cards from the get well is equal to 1 over 40. So that means that if 1/40th is 5, then 40 40ths is going to equal 5 times 40, which is 200. So 200 cards altogether. Now, if we know that there are 200 cards altogether, then what I know is then that 5 plus x plus 3x plus minus 1 equals 200. So then if I then simplify all of that, I get 4x, and it's going to be minus 4 plus 4 equals 200. So 4x equals 196. So x equals 49. So then from this, what I can then do is, now that I know what x is 49, this is going to be 49, and this is going to be 3 times 49 minus 1, Now, in terms of the birthday, which is what the question's asking me, well, if I then work that out on my calculator, 3 times 49 minus 1 is 146. So then that's going to be 49, this is going to be 146. Then working out the relative frequency, it's going to be the number of times its birthday card, which is 146, over the total number of trials, which was 200. And then we can simplify that fraction as 73 over 100. Or you could write it as 0.73. So any of those three would be fine for the full marks. Then moving on to question 14, it says, in a university there are 150 historians and 80 philosophers. The probability that a male historian is chosen at random is 0.36, and the probability that a male philosopher is chosen at random is 0.7. One person is chosen at random. Show that the probability that the person is male is less than 0.5. Well, if we look at this information here and the 150 historians, so let me just start by writing a heading of historians, that we know that the number of males is going to equal 150 multiplied by 0.36, which equals 54. So that means that the number that are female is going to be 150 minus 54, which gives me an answer of 96. Now I'm just going to put a little bubble around that, and I'm just going to highlight these two bits of information. So then if I do the same, but this time for the philosophers, so here the probability that they're male is going to be 80 multiplied by 0.7, which gives me an answer of 56, and therefore the number that are female is going to be 80 minus 56, which is 24. Let's put a little bubble around that. Now, in total, we have, so the total people is going to be 150 plus 80, which is 230. So therefore, the probability of selecting a male is going to be a total of the males, which is 54 plus 56, all divided by 230, which gives me an answer of 110 over 230. And if I convert that into a decimal, it becomes 0.7478. So as you can see, 0.478 is less than 0.5, which is what they wanted me to show. Then moving on to our last question, it says that a sweet shop makes milk and dark chocolates. The probability that of selecting a milk chocolate at random is 0.6. The chocolates are randomly sorted into boxes of 30. Work out the expected number of milk chocolate sweets in a box. So for this, all I need to do is just multiply 0.6, multiply that by 30, in which I get the answer of 18. Then moving on to 15b, it says Lucy checks the chocolates in one of the boxes. She finds that it contains the expected number of milk and dark chocolates. She eats 2 of the chocolates at random. Shows that the probability that both the chocolates were dark is more than 0.15. Well, for this question, let's first of all work out what is the expected number of milk and dark chocolates in this box of 30. So the box contains 30 chocolates. So to work out the number of milk, well, the probability of selecting a milk is 0.6. So if I multiply that by 30, it's going to give me an answer of 18. Then for dark chocolates, the probability is going to be therefore 0.4. Multiply that by 30, and that gives me an answer of 12. So then the probability that her first chocolate is going to be dark is going to be 12 out of 30. Then she's eaten a chocolate, which means that there's only going to be 29 chocolates left. And how many of those 29 chocolates are going to be dark? Saying that she's eaten 1, well, that's going to be 11. So then all that's left for me to do is do 12 over 30 multiplied by 11 over 29, which gives me an answer of 22 over 145, which as a decimal gives me 0.1517, blah, blah, blah. And then when it comes to show that it's more than a number, all you need to do is just do the answer of 0.1517 0.517, make sure you have a few digits after the 0.15, is greater than 0.15. So there we go. So it's really important that when you're going through these types of questions, don't know why I crossed that out. When you're going through these types of questions where it gives you a value that you want to show is more or less, then make sure your last line in your answer looks like an inequality where you are proving or disproving what they've actually asked you to show. Then moving on to the last question, it says 15C, 2 dark chocolates were replaced by 2 randomly selected from the shop. Explain why the probability that both of these chocolates are dark is different to your answer in part B. Well, there's a couple of things you could say. You could say that the chocolates could be replaced by either dark or milk chocolate. And you could also say that probability of selecting 2 dark chocolates is going to be 0.4 times 0.4, which is 0.16, which is different to the answer in B. So something along those lines would be fine. You don't need to give both those statements, just one would suffice.